Good afternoon, good morning. I guess everything works. I'm live. A little bit late today because you believe or not, I forget to set up the event for the live stream. So the StreamYard, the platform for streaming, didn't allow me to enter the studio because there was no event planned. Anyway, we have a lot to do today. I will start with the USB power delivery IC for the 5V 3 amp or more than 3 amps, let's say the maximum current allowed for the 𝗶𝗶𝗶𝗃𝗃 device. To be sure, let's say we need 3.3 because 3.3 is power supply for the entire thing. 5V is for HDMI, so we need 5V. If we go over 5V from the USB power delivery, we can go lower with the current, but I don't want to make the thing more complicated than it actually is. So I will stick with the 5V. That would be the nominal voltage for 5V devices, relay and HDMI, and yes, and the USB OTG ports. So yeah, now let's check the power requirements again for the compute module, which is, I don't know how many amps they need. They say 7W at full load from 3.3, which is over 2 amps at full load. And as I checked, the maximum current of the USB power delivery IC is 3.25, which should be, yeah, there will not be much headroom for that. I don't like it. But on the other side, I want to use the 5V USB power delivery adapters only because the more complicated ones are I'm unsure now. Anyway, I need the 𝗶𝗶𝗃𝗃 device, so let's start with it. In the meantime, I checked that there is a symbol created in KiCad already, so I copy the symbol. Into my symbol library, and this is it. Yeah, and since now I will modify my symbol, not the system one. Let's say this. Yeah, here is the English. I found the Chinese data sheet at 𝗗𝗲𝗃𝗃𝗃𝗃 database, but the Adafruit has the English version of it, so it's more convenient. And you can see the ISET current at max is 3.25, which from 5 volts is 15.75 watts. And when we allocate 7 watts for the USB for the compute module, there is more than 7 watts for the rest of the system. Yeah, I will keep it at 5. Good afternoon, Arun, Vignesh. Thank you for being here. Thank you for watching. So let's continue. Symbol. So I can keep the English version of the datasheet. That's even better. I'm going to simplify the description. And I have to check the the footprint of the device, which is DFN10 and 𝗬𝗲𝗃𝗃. I don't understand. At JLC-PCB there is this one, which is DFN10, and this will be my device. So DFN10 3 times 3 millimeters. That's our device. Okay. So yeah, this, but I need to copy the footprint into my library if it isn't already there. Manufacturer's order code. I can keep this because it's a valid universal name. Supplier. Let's check. I don't know if standard suppliers sell it. I think they don't. Yeah. Mouser, no, and DigiKey probably not. Okay, so the supplier will be JLC-PCB with this C code. Yes, USB, no, USB PD. Yes, USB PD is quite fine keyword. Now the footprint. Before I check the pinout. Let's continue with the footprint to finish the job I started. Thermal vias. Let's check what is the recommendation of the layout or footprint. If it's something in here, no. Okay, just the typical application circuit with the P-MOSFET, P-channel MOSFET here. It seems that, yeah, the 𝗬𝗲𝗃𝗃-6 is for cable and we want device. So, okay. I will use the footprint without thermal vias because it's this IC is only a controller. The power will go through the MOSFET. Let's check the 3D model. missing, but I think because of the exposed path specification here, so let's check the package DFN. Package DFN here. We are looking for WDFN or DFN. It can be DFN if it's 3 times 3. For instance, this one. Naturally, the exposed path on the 3D model is not important. We want only the same pitch and the same dimension of the package and the same pin count, of course. So this model can work, and works very well, as you can see. So, okay, let's keep it. Now to assign the footprint to the symbol, there are 2 ways to rename the library to Daemon, which is my library, or search for the particular footprint name, as I did. Okay, pin check. Number 1, input voltage D plus D minus 2, 3. The input D plus D minus, okay. CC1, CC2, 4, 5. Okay. Ground is 11. Exposed path, yes. SDA, SCL is 6, 7. Yes. And we set 8, I set 9. We set 8 and I set 9, yes. And gate is 10. Gate for the PMOS transistor. Okay. What about the MOSFET? Is there any recommendation? Probably not. So I will use the standard, let's say 30 volt PMOS from my library. Fine. We have symbol, we have footprint. Let's check the symbol. No issues found. Perfect. So we can go to power, place the footprint here. Okay. This one. Okay. We need the power. This is boot port, which will, let me think, can we use the boot port for the powering the entire thing, for powering the entire thing? Just, yeah, we can only in case that the boot port can supply the board, of course, because currently we use the V-bus signal of the boot port only to control the USB multiplexer. No, I decided that I will add another USB port. Okay, I have to assign the JLC code after that. Okay, so another USB port, because no, it won't be elegant. The thing is that if I connect the power delivery USB adapter to the boot port, it can be, the output voltage of the power delivery thing can be, I don't know what. Yeah, there are some standards, but yeah, we have to be 100% sure that there won't be 9, 20, I don't know how many volts. Okay, I will use another USB Yeah. Yeah. Okay, yeah, I will. So this won't be a boot port, it will be USB PD port. This won't be here, and we need to create more space for it. Yeah, there is a thing that the PESD2ETH is not available anymore because, or last time I checked it, it wasn't because of an Xperia thing. Let me check it. Zero stock. Yes, we have to use separate diodes because this doesn't work anymore. Okay, D plus, D minus, D plus, D minus, D plus, USB, D minus, and D plus. Okay. Here will be ESD diodes, 5 volt, this one's the small ones, with low capacity. Okay, more space for the designator. I can go higher, nice. And three rounds. Okay, let's continue. CC can be connected directly to the controller. Yeah, we can. Even the minus port and plus port. I assign the label because I need to assign the net class. Okay, it seems that there is DP100, 100, watch, 90. Oh, I'm not sure. I'm unsure now. USB impedance per 90. 90, is it? Yeah, 90. Okay, yeah, I was unsure for a moment. 90 and 90 here. Okay, here will be ground. Yeah, I'll move it closer because it was like crazy tone. I set, as the datasheet says, can be left floating for the maximum current, but it's not very systemic, isn't it? So I will place a footprint placer only with, I don't know, 33K, and this resistor will be not populated. So 33K. Why? Okay. And as I said, the symbol or footprint will be set as non-populated. A little farther from the IC. And the voltage. The voltage won't we want 5 volts, which is 0K, 0 ohm. I will place 0 ohm resistor, not a direct connection with ground, because there can be some changes in the future, and frankly, I'm still unsure if the nice would be to make it universal. So for the 5 volts, the 5 volt voltage of the USB power delivery port will be used for the 5 volt domain. Naturally, with the higher output voltage, there will be a buck converter from, let's say, voltage higher than 5 volts to 5 volt, and yeah, and for the simplicity, there can be a short circuit 0 ohm resistor if the buck is not populated. Yeah, something like this. Let me think. I don't know. If you have a better idea, please give me a comment. I am unsure. I'm unsure. Based on the wattage, based on the nominal power, it should work, but with quite low headroom, and that's what I don't like. The very little headroom. So this is for iSet, and this is for VSet. Yes. SDA, do we need SDA? I think we don't. Operation with I2C. Yeah. The hosted MCU can, or the system MCU can visit the IC registers through I2C bus and select the proper PDO to request from external PD source. As the highest, yes. So you can set the output voltage and output current through I2C, which overrides the VSet and iSet resistors, but we don't need the I2C. As they say, can visit, not must visit. So let me do something like this. 2 test points. Small ones. Okay. SCL, SDA. We of course need pull-up resistors, so I will use 3K3 on both. And I will bias them to 3.3, which is 3.3 is here. Let me, there's no, these old symbols are, yeah, 6 volts is the maximum input voltage. So in the case of the higher output power USB power delivery adapter, it won't work. We need something different. Ideally, we need a buck converter with some power path, which means that when the input voltage is the same as the output voltage, the internal MOSFET is constantly on, and we need or we can have the input voltage at the output. It means that the buck converter must allow duty cycle, the maximum duty cycle, to be 100%. We can check it. For instance, this one, which was used to change the 24 from the previous design to 5. Let's check it, just for the sake of yeah, we will be smarter. Duty, let's say duty cycle. No. Let's find duty cycle. Maximum duty cycle is 97%. Yeah, it means that from 5 volts it could make 4.85, which is not so bad, but not so good. Yeah, let's check. Yeah, I will finish this because I am like ADHD. I'm not, but sometimes during the stream I feel like the person with a spectrum, because there is so many things you have to take care of, the commands, the camera, the yeah, I won't overcomplicate it. So yeah, the buck converter. Yeah. The buck. Let's check my bucks. I don't have many of them. TPS, this one is a nice one. I love this TPS 5450 or 5410. This one is 5 amp, this one is 1 amp, and they have 5430, which is 3 amp. So let's check the 5 amp. What is the maximum duty cycle? Yeah, this is the 5.5 to 36, so we don't need to check it because the input minimum voltage is too low. This is from 4 to 36. We need a powerful buck because it will be the buck that converts the input voltage or the output voltage of the USB power delivery thing to 5 volts, and then hi Alan, thank you for the question. No, it doesn't. If you the distance of, we can calculate together later, but no, the distance between the IC and the connector will be like 1 centimeter. It doesn't. Yeah, the wave action won't happen there. So no common mode chokes. No. Just be careful with the differential pair impedance of the traces. Thank you for the question anyway. Thank you for watching. What I was doing, I was looking for a buck with at least 5 amp at least of the output current, with input voltage of ideally 4 volts to 30. I don't know if you hear the noise, but yeah, it's like wash machine goes crazy of some apartment near me. Anyway, Of course, I can use any buck converter from the market. Yeah, so. But I like to use my ones because, you know, too big. What's maximum current of this? It's a synchronous. No, 0.6. Oh yeah, 0.6. I'm blind. I'm getting blind. 4 amp is this one. This is the one I am using. No. Oh, I don't want to compromise the design. I want to have it. Yeah, what I hate on KiCad is that when you see what it does, when you double click the thing or go to preferences, the description column gets narrower. This is 5 amp buck. What is the maximum duty cycle of this thing? This is synchronous, 5 amp, adjustable frequency. Wait, 14050. That's the one I have already. Yes, that's the one I have already. So 97% of the maximum duty cycle. $5.5. Watch it. This is what? This is 5 volt, 5 amp step down for 4.5 to 60. In some, I don't know what this. Yeah, that's normal. That's quick. Let's check the data sheet. What for the maximum duty cycle? If it won't work, I will use the one I am in the schematic right now. I don't want to spend my life working on it. Yes, duty cycle. When operating with a low voltage difference, that's exactly what we want to solve. With a low voltage difference from input to output, the high side MOSFET of the thing operates at 100% duty cycle as long as the boot to switch to switching pin voltage is greater than 2.1. When the voltage But how to make the boot to switch voltage difference always greater than 2.1? No. You know what I don't like? I don't like the fact that even the tolerance of the output voltage of the USB power delivery thing can be something, non-zero tolerance. So it means that from the USB power delivery we can get, let's check it. We can get lower voltage, but there is a standard. And when there is a standard, all USB power delivery things on the market should should comply with it. Yeah, 5% they say. Okay, so when we get 4.75 and the thing has 97%, it's 4.6, which is almost at the lower tolerance of the 5-volt CMOS logic. So not good. But if I directly set the voltage to 9 volts, it means that we can't use the 5-volt adapters at all, which is quite limiting. You know what, I won't overcomplicate things. I will keep it 5-volt only. 5-volt will be the output of the USB power delivery port, and there will be only one buck from 5 to 3.3, which can be this 1 2 amp. Yes. No, this was 24, 5-volt. This is what I want. Yeah. So let's finish the USB thing. We need the PMOS and we need a discharging resistor. Let's use the same configuration as they have here. I'm not sure if the 50K, okay. So PMOS, another thing. We need some okay, we have to create a new package, a new symbol. I don't have suitable MOSFET in my library. Yeah, PMOS. At least 30 volts, at least, I don't know, 5 amp. Let's check. Okay, MOSFET, let's start from here. No, this is MOSFET, what the book. No, kit. How to, yeah. So we need in stock, active, P channel, drain to source. Yeah, let's do this because we need drain to source at least 30, let's say to 100. Continuous drain current 5 amp at least, let's say 4 to, I don't know, many. Let's see, we want MOSFET, we want surface mount. Let's see. Yeah, DFN 5 to 6, something like this, I would like. So let's, but yeah, the bigger one. Let's start from the most available ones. Something like this. Or Siliconics. What's the size of the package? It's a power pack. Threshold 3 volts. I don't know what transistor they recommend. There is no mention of the FET. No. The Adafruit thing uses, yeah, something similar, but I didn't find a schematic of this thing. Maybe somewhere. Do you know downloads? Yeah, here is schematic. Okay, so let's see. Yeah, they kept the 49.9K. Okay. Yeah, we need the decoupling capacitor. Yes. And they use AONR 21307. So again, AONR 21307. AONR 21307. That's the thing. Yes, 30 volts, 24 amps, similar price. Threshold 2.3. Yeah, near the middle of the 5 volt. That makes sense. Okay, okay. I will use the same one as Adafruit. DFN 3.3. Okay, nice little package. Nice. Nice one. Yeah, I will use it. Alpha and Omega semiconductor. Okay. So we need a symbol. Yeah, for instance, this one. Save as. So we need part number, data sheet. We will need the JLC PCB code. Yeah, well available in China as well. Okay, and the pinout will be changed in a while. So let's continue. This is the part number. This is not dual. This will be a different package. Datasheet. This is only P channel. 30 volt, 24 amp. 30 volt, ED, 24 amp. VGS is 2.3, they say. The threshold of the VGS. Typical 1.8. I'm always using the typical values. Not 1.8. Yeah, it's not SOIC, it's DFN. No, DFN. Yeah, DFN 3.3. DFN 8, 3 times 3 millimeter. The part number is this one, the KiCad B, and JLC code is this. I didn't copy the code. Yeah, probably not. This code. Yes, and now to the footprints. Yes, I want. Let's check the footprint. DFN 3.3, DFN 8 3.3, exposed pad, something like this. But let's check the. No, it's different. That's different. This is different. It's a power DFN, so we want bigger drain side. PDFN. I think I thought I had something. I have only this one. Okay. Issues, only issues. There's no example footprint. This is not I thought that. Don't tell me that the KiCad doesn't have. It's 8-pin package, isn't it? Yes, 8-pin with the large drain area. That's a super normal, super common package. I'm confused. Okay, no, I have to. Another option is here to adapt some model. Yeah, that's pretty nice footprint with nice model. Okay, I will copy it. That. Oh, yes, it's me. Applications. Let's do the thing. The step file is here. It's dfn8, 3 times 3 millimeter. Let's put it there into my library, 3D models, and symbol. We don't need symbol. This is our footprint. So I will close it for a while. This is our symbol. Pin 4 is gate. Exit sync mode. Gate is 4. We have 3 sources. Which is source 1 is pin number 1, 2, 3, yes. S1, S2, 2, and S3, 3. And I make these two invisible to allow to stack them, as well as here the drains. No. And the drain is 5, 6, 7, 8. So 5, D1 is 5. D6, D2 is 6, but invisible. D3 is 7, invisible. And D8, D4 is 8, invisible. Okay, so let's stack them. So the symbol is ready. Now the footprint, input, passive, passive, okay. Footprint, let's set the footprint libraries. We need to add, project specific library I already have, the KiCad pool. This is the location where I put the file, but it's 21.307. 21.307. This is our footprint. Yeah, I like it. That's a lovely package. The only thing is that they call the entire polygon 5, 6, 7, 8, which makes the symbol incompatible. So I will set only 5. And the symbol will have only one drain. Yes, only number 5. So number 1, 2, 3 will be sources, 4 is gate, and 5 is drain. And I need to copy it into my library, and it's dfn8, 3 times 3, I set fat millimeter. Okay. So dfn8, this is our thing. Yes, let's assign the 3D model. I am expecting that KiCad crashes because it always does when I assign new 3D model. dfn8, but in my CD model library here, DFN, I am missing the search field here. See? Pink. It's annoying, but yeah. DFN8 here, this is our model. Now it didn't crash. This is our footprint. The details of the footprint, okay, empty. That work for me. 21307. Don't hide. DFN8. This one, yeah, this is our new symbol, footprint. Okay, okay, okay. Let's call the checker. No issues found. Let's get back to footprints. Let's call the checker as well. No issues found. That's a good message. Now we can place it. Okay, we have to open the schematic before. So now, and the, let's clean a little. Oh, we have 𝗲𝗀𝗃. So source, of course, is at the input to connect the blocking substrate diode. 20607. This way. 50K or 49.9 and 5K1 to the gate. 5K1, yes. And 49K9, I don't have. I'm not sure if this value is really needed, but I think the data sheet it's just the resistor keeping the FET in a discontinuous mode when the gate is high or floating, and it makes and creates a voltage divider with the 5K1. I don't think we need this exact value. I will place 51K if I have. Yes. This FET doesn't set any output voltage. It only enables the output voltage of the V bus. Yeah. So I think there is no point of overcomplicated thing with it. And they say, yeah, there is like, yeah, that's definitely a good idea. I like it. I like it. Yeah, that's always a good thing. For limiting the short circuit current if anything happens. For second, it allows you to disconnect the input voltage from the IC if something happens with the board and you need to debug it. So 100% I agree with placing the resistor there. Good design. That's definitely a good design. But now I'm thinking if, yeah, I use the same, but the material is X7R. Okay, no problem. That's class. Yeah, class 2 material, but really quite stable. No much of a tolerance. Temperature stable. Yeah. See, I hate this line going through the. So this is our thing. Okay, and this is the output voltage in our case. 5 volt. Yes, and we will place something like this to allow us to isolate the output. Yeah, we don't need the signators here. Okay. Yeah, definitely here will be ground. Long ground wire. So at least let's make the resistors to be aligned. Okay. Something like this. Diodes are here. PTC here, definitely needed. Okay, so we have our power delivery thing. It took an hour. I am unbelievably slow today. I think every day. Okay, you know what? Keep it. Keep where you are. Okay, the buck converter 3.3. What I'm going to do is the clear annotation of this selection, pink. So we have 5 volt input, a buck converter 3.3, output LED, as well as here the isolating resistor, 2 test points. That's a good idea to place the second one here, because when the 0 ohm resistor is out, we want to measure the output voltage as well. Okay, so this can go, we can get rid of this one. Let's make this drawing like this. Okay, we have MOSFET, we have powering of the IC, we have CC, we have USB D minus on D minus, D plus on D plus, assigned net classes, ESD diodes on both, on all, not on all. We have to add 2 more because we have CC1 and CC2, which are signals of the same sensitivity as the other ones. And we really don't want to risk the health of the CC1, CC2 signals, which is extremely important, like crucially important for the power delivery thing, because through them the controller set the output voltage on the port. Okay, we have power. Yes, we have power 3 point, we have 3.25 amp, 5 volt, and we have this is 2 amp, which is not enough. This is not a good buck. We said we need 7 watts, so it means we need 2.1 amp. Okay, so let's continue with this. We have to replace the buck with more capable one. That one I just deleted was fine. This one. Yeah, for the price that I had to add the ESD diodes again, but it is something I want. Yeah. Selection, clear annotation, okay. Frequency selection, enable can be put to the input. This is not VN. This is no 5 volts. We can use smaller caps here. Yeah, X7R in a reasonable size. This is, yeah, you can say that I can design anything. I can create new symbols. Yeah, I can, but yeah, as you know, I really love to reuse what I did in the past, because to blow up the library, that it's not what I want to do. 3.5 FB, 3.3, sorry. We have to recalculate the divider, but this will be easy. Yeah, this one can be copied from here. Like this. Yes, now we have 750 feedback. Let's check it in the data sheet. Feedback voltage 750. Let's call my thing spreadsheet. So 75, what? New numbers, not now. Okay, 75 is my output voltage, and one of the resistor is, well, let's say 12K. We will work with it, but let's do it 12K. 40, 120, 43, too much. If we say 10 and 39, let's use this. .3, 34, which is not in the range. 11, 7, 41. This 15 and 51. That's in the standard R24, I think, range, which is in which I have on stock. I don't need to buy anything, as you know. I don't want to blow anything, including my stock of the components. My component stock. My component stock needs to be protected. There are 4 caps of 1 micro. See out. Yeah, they didn't calculate the inductor, but yeah, I think we'll be fine. We have slightly lower current, so yeah. See out, they say no smaller than 16 micro. Okay, I will use 2 of them. How much does this thing cost? It will be bargain, not bargain, it will be fortune, I think. $1 one. I think we have to use something different. This one should be rather expensive, X5R, but not much, $1 almost. So this one, let's try this one, $0.50. Yeah, X6S. Okay, sounds good. I will use 3 of them. Go away. We need 47 micro. The material is not important now for the search. Yes, Murata X5R, it's slightly worse. This one, Murata 18,025, 21 cents. That's a good cap. Yes. So 47 to 16. Let's check it. Not check it. Let's change it in the schematic. They say by this equation, I don't have time to recalculate this at the moment, but okay. Okay, 4 of them, 47 micron to 16. This one is the one. Yes. Change the value for all 4 of them. Yes. This is the freewheeling diode because the converter is not synchronous, which is not ideal, but I don't know. I will maybe in the meantime I will think about it. It's not quite an expensive one, and it's not synchronous. Yeah, that's the tags for the white input voltage. We don't need this white output voltage, but I'm losing myself in this buck thing. Yeah, I can use something like this. This is 3 amp output, but if we change the output voltage, it won't work. And this one will work. I will keep it. To have the buck converter able to work reliably with some reasonable headroom for current is always a good thing. That's not a bad design behavior to keep reasonable headrooms. We can change this, the frequency. The one thing is that the buck is not synchronous, so we need a rather big freewheeling diode in power die package, but there are worse things in life than this. Okay, power supply can be done. I call it done because this way I would spend 1000 hours here. This is our GPIO, and I think in the rest of the time today I will assign the labels to the header. Yeah, for instance here, it's unofficial page, and I want to use schematics. Let's check the 4 Raspberry 4. Where is the header here? No. I don't know if KiCad can import the picture from the... No, it can't. It can't. We have to save the picture. I can clear my mess. Downloads. Where is the thing I just downloaded? Oh, on the desktop, yes. Here. We are here. Pics. Oh, I can see that I already have a nice picture of ports, but I will use the new one from the newest schematic of the Raspberry Pi 4. Raspberry Pi 5 doesn't have schematic released, maybe somewhere else. Okay, so number 1, let's roll up our sleeves 3.3. 2 for our 5 volt. We have number 9. Is ground. I have to move it further from here. Yes. On the other side, number 6. Even more. Yeah, number 9, 25 to 39. And on the other side, 14, 6, 14, 20, 30, 34, and that's it. Okay. Now the labels, or the nets for the ports. Now this one, I will copy this one just to mark the length. I want the same length. Okay. Okay, so GPIO 234, sorry, GPIO 2 here, 3, 4 to 7. Now, is there? No, there is no such a thing as a sequence. So 13 is GPIO 27. 15 is GPIO 22. Oh, what? $19 is GPIO 10. 21 is GPIO 9. 23 is GPIO 11, 27 IDSD, GPIO 5, on number 29, 26, 39, 20, GPIO 6, 33 is GPIO 13. I'm in a hurry and making mistakes. 33, 13, okay, 35, 19, 37 is 76. Okay, the other side. GPIO 14, 10 is GPIO 15. Okay, so I can call repeat the action. Now GPIO 18. 16 is GPIO 23, 18 GPIO 24, 22 GPIO 25, 24 GPIO 8, 26 GPIO 7, 28 IDSC, 32 GPIO 12, 36 GPIO 16, 38 GPIO 20, and 21. But we are not done with it because, as I remember, I wanted to use some logic isolator for this to protect the GPIO ports of the Raspberry Pi. So it won't be so easy. Yeah, next time. Let's update our to-do list. We have USB power delivery. We have 3.3 buck converter, but it cost like 1 liter of my blood. Battery backup we don't have yet. Advanced GPIOs, as I said, next time. Believe me, I would like to spend hours with you here, but I can't. Next time I will be better. Let's check the buffer. Let's check the digital buffer we will use next time. Something more than single gate, of course. Something like low expensive, something like PCB layout friendly. This is inverter. No, this is buffer. And ideally, input on one edge and output on the second edge of the IC. The hex buffer is fine, but it's like, let's say, unfriendly pinout. Something like this 3-state buffer, that can be the thing, because it's a commodity thing working from 1.6 to 3.6. That's good. We have 3.3 ports. What we can is to make it 5-volt compatible. Do we or not? If not, we can use this one. Let's check the pinout exactly. No, this is not what I wanted. Oh, I was checking different package. We have 𝗗𝗲𝗀𝗃𝗲20. This is this one. A0Y0 to A0 to Y0. I'm lost. $416. Okay, there are 2 ports. Oh, I see. There are two groups of 4. Which one? The first one is oriented from the left to right, and the second from right to left, which is not we want. This is not our thing. This is the standard single, not single. This is not single, but not the pinout I want. This pinout is good as well, and this is port. This is voltage translator. That can be fine because the Raspberry Pi is 3.3, and sometimes we need the voltage translation to 5 volts, for instance. We have 5 volts on the board. The maximum voltage of the high voltage side is 5.5. Yes. Both sides are for 5.5. Okay, let's check the pinout. The pinout is perfect. Wait. We need. There are not inputs and outputs. There are GPIOs, input and outputs, at the same time. But this distinguish between. No, this is transceiver. Yeah, this is transceiver. So that works from both sides. This is exactly what we want. Yeah, as you can see, the structure is mirrored, so from both sides can be input and outputs are it's transceiver. This is our thing. How much this piece of gold cost? I guess $1. $2.15 is too expensive. Why is so expensive? I thought that it used to be least less expensive. From China is 85 cents. That's better, but I don't know. It's a good thing. It's exactly what we need. It's voltage translation. It's pinout compatible, pinout friendly. But do we need the voltage translation for the price of how many outputs do we have? I can close this. How many ports do we have? On this side there are like 6, 9, 14, and here 5, 9, 12, 14 and 12, 26. It means we would need 4 of them. $10 for the feature that is just nice to have. I'm unsure. The price destroyed me. Let's see. I will put this because we spent again a lifetime working on it. Yeah, in comparison, this is a standard Schmidt stage. Yeah, pinout like awful for our case, but the price is 7 times lower or 6 times. So it means that 4 of them, this is six element thing, so 26 we said, so we would need 5 of them, $1.65. That's a reasonable price, still lower than 1 package of that thing. C. On the other side, I'm putting here this one. We will have multi-layer board, so yeah, the interconnection won't be an issue. Let's see. We have something to think about until next time. We will finish the schematic next time and start working on PCB layout. I'm sorry for confusion today. I was a little bit tired, but I think we did a good job. We are 1.5 hour in the show. I think it's good time to stop. Thank you for being here. Thank you Yasin. Thank you for watching. See you next time. Bye bye.